What I want to do today is look at a set of problems that I've seen on Piazza in particular and focus in on angular momentum and slender rods. There are a number of questions on past quizzes and exams. So the learning objectives here look at angular momentum and slender rods, in particular slender rods that are falling, and understand that while the motion may be complex looking, it's relatively straightforward. I have a uniform slender rod AB, which has a mass of 2.3 kilos, length of 0.75 meters, and it's dropping. And as it drops, it comes into contact with the corner. And when it comes into contact with the corner, the smooth corner, it has a velocity V1, which is 2.5 meters per second, and no angular velocity. Determine the angular velocity of the rod immediately after impact. Now, I know this is an angular momentum problem because there's moment, velocity, and time, so it's going to be an angular velocity. First thing I do is calculate the moment of inertia about the center of mass, I sub g, which for a long slender rod, you're used to this, 1/12 ml squared, and it's 0.1078 kilogram meter squared. So before impact, I have a translational velocity. The rod is falling and it has a velocity at the center of mass V1. It's translational, so all the points on the body are going with V1. When it hits the corner, it's going to have a reaction force, and that reaction force is going to be given to me as ax dt, ay dt. Now, I'm not given the time that this occurs over. I'm just sort of saying it's occurring at the center, but I'm doing moments about a, so that's not going to play a role. There is a weight term in this, but generally with weight terms, I ignore them because they're insignificant. It might be more important if I got a time associated with this, but I'm going to assume it's relatively short time. And finally, it's going to have an angular velocity, which is going to be given by ig omega over here, and a translational velocity, which unlike the previous velocity, is now normal to the rod. So this thing is rotating about point A. That's my instantaneous center. And V2 is equal to the L rod divided by 2 times omega. So I can do that. So I will have a translational component, that is mv1 L rod over 2. That's the times sine beta. That's going to be essentially a moment arm of the linear momentum plus 0, which is the impulse, which is going to be 0 because it's acting, A is acting 0 away. Here I have the angular momentum, and here I have the linear momentum times its moment arm from the center. I can't do it at point A really. It's not, I mean, I could, I suppose. And in fact, I end up doing exactly that. Maybe that's what I should say. So I could probably just use, in this case, the parallel axis there. And if I did that, I would get the same result. So all that does is that it changes this term right here. So V2 becomes L rod over 2 times omega. So I now have L rod squared over 4. Substitute it in, put all the terms in. I get an omega, just dividing one side with the other, of 2.5 rads per second. I want to investigate a new launching system. So I've designed an experiment that is going to use a uniform 2 meter by 8 meter rectangular plate with a mass of 4,500 kilos. Knowing that the plate is released from rest and falls vertically 2 meters before the cord becomes taut, determine the angular velocity of the plate immediately after the cord is taut. There you go. So I have here a plate, and that plate is given to me as having a length of 8 meters, a height of 2 meters, and this line here is representing a rope that's not taut. I release it and it drops, and very cleverly with this animation you can see it drops down to here. And the distance that it drops is 2 meters. So I could do it from center to center, top to top is just easier to show. And so if I continue, I can calculate my moment of inertia for the plate, and that plate is going to be 1/12 mass of the plate, a squared plus b squared. This is something that if we were on an exam, we'd of course give it to you for the moment of inertia. So we'd say 1/12 mass of plate, a squared plus b squared, or we'd give you a number, say mass of the plate is 4,500 kilograms, and here's a radius of gyration that just happens to equal 25,500 kilogram meters squared. Since it starts from rest and drops 2 meters, I know I can use work energy here, so it's T1 plus V1 equals T2 plus V2. T1 starts out at 0 because it's zero velocity, and when it drops to the low point, I'm going to call that 0 also. So initial potential energy equals final kinetic energy. So mass of plate GH1, 1/2 mass of plate V squared, and putting all of it together, you get the standard equation, which you've seen, V equals 2 GH1, which is equal to 7.62 meters per second. So again, this is a case where you just have to draw out the diagrams. You have the initial linear momentum, mv. You have a reaction force that's only really coming from the chord. Again, you're neglecting the weight. And finally, you have the resultant velocities and velocities in linear and angular. So if we start with the x momenta, we start with 0 in the x direction, 0 impulse delivered in the x direction, vgx prime, which is what I'm calling it, is 0. Moments about point B, I have ig omega prime plus mvg prime a over 2, and I have mv a over 2. From the kinematics, I can say omega a over 2 equals vg prime in the y direction, and calculate my moments about B. So it's ig plus m a over 2 squared times omega prime. Substitute all the terms, and you get out of this mv a over 2 equal ig plus m a over 2 squared equals 1.4164 rads per second. Again, writing units down helps because it's hard to do these types of problems, say on an exam, writing variables. Best way to do it is writing variables. Really, you can't make as many mistakes. I don't make as many mistakes that way. But if the second choice, and it's always a good choice, is to write the units down on all of your terms, so you make sure you keep track of things. Draw your free body diagrams, draw your kinetic diagrams, draw your kinematic diagrams, draw every diagram you can, and don't imagine forces that aren't there. There's a tendency to look at problems like this and desperately want to have a force that you imagine or you intuitively imagine exists, and it doesn't. Don't do this. Just draw what's there. Here's a reference that if you're bored and you want to look it up, it's great. It's Colombo. Just the facts, man. Actually, I think that's a much older show, and I have to Car 47 or something. It's from the 50s. It's one of the actors was Harry Morgan. But anyways, don't imagine forces, just the facts, nothing else. Identify these problems right from the beginning. You have force, velocity, to time. It's linear momentum. Moment, velocity, time. It's angular momentum, and you can do these